So we'd like to welcome the next speaker, Dr. Debashis. So while he sets up his presentation, would like to introduce him. So he is a joint assistant professor of computer science and engineering, as well as his pediatrics at the University of California, San Diego. He's an engineer by training from alumni of IIT Kharagpur. Went on to do his PhD from Stanford, and his research interests are quite varied. So he's interested in analysis of biological systems, majorly with reference to B cell differentiation, colon cancer, bladder cancer, and prostate cancer, as well as formal verification of hardware designs. One of the major successes that he's been credited for is for identification of a conventional chemotherapy for colon cancer, and this actually got published in the New England Journal of Medicine in 2016. So thank you, Debashis, for being here. And yeah, so the stage is yours. Would you like to share your slides?
All right. So I'm going to start my talk on AI-guided discovery of barrier protective therapy in inflammatory bowel disease. I'm going to talk about a new approach to solve problems. In general, how do you identify targets in a particular disease? And here I'm going to give an example of IBD, which is inflammatory bowel disease. But mostly the method can be applicable to a variety of other situations. If you think about the traditional approach for target discovery, you start with data. In the disease setting, you start with the normal sample and a disease sample. So two groups of samples. And most people, when they have this data, what they do is they try to identify genes that are differentially expressed and hope that the target is buried in this large list of differentially expressed genes. Other groups build a really complex network of relationships. And they stare at this network and try to come up with the properties of the network and figure out which gene would be a better target for the disease. In these analysis, the underlying relationship that people are thinking about between genes are mostly symmetric because you can see the network don't have any kind of edges that are directional. They're all undirected edges. It's very hard to figure out directed edges. There has been attempts to convert this graph into directed edges, but mostly in terms of hierarchy. But the relationship underlying is basically symmetric. I'm going to introduce a new approach, which is also simple. Instead of characterizing relationship in two category, which is equivalent and opposite in this term, or positively correlated or negatively correlated genes, we're going to divide this relationship into 6 different categories. I call it Boolean analysis. The Boolean analysis is basically a mathematics of two values. So anytime you do mathematics of two values, you call it Boolean. In this case, we are looking at gene expression data, which is continuous. We're going to discretize this into high and low values. So there is a way here we call the step minor. It tries to fit a step and divide the gene expression values for any gene into these high and low values. After this point, you look at every pair of genes and figure out what exactly are the relationship between those genes. And the situation here would be when you have these high and low values for these two genes. When you look at a scatter plot or a relationship between two genes, you have 4 different quadrants. And in order to identify a relationship, what you do is try to identify a quadrant that is sparse. So in the context of this positively correlated and negatively correlated genes, you would see two quadrant spars, which is the top left here and bottom right here. For the opposite, you have the top right and the bottom left quadrant spars. But there is a variety of situations where only one quadrant would be sparse. These are the bottom four panel. And you can see on the left side here, top left quadrant sparse. In most of these situations, you can see they have weak correlation. They don't have a really good correlation. So they would be ignored in most other situations. Whereas I'm going to tell you that these are the most informative cases where we can actually use them to come up with targets. In some of these cases, you can see the correlation even be better than, you can see the opposite relationship here has a correlation of minus 0.67, whereas this relationship where we call it high implies low, XIST high implies RPS4Y1 low, has a better correlation than this one. The correlation is misleading because it doesn't give you the picture of asymmetry. It gives you how in general they would be related, whether positive or negative. But even when you have a really strong asymmetry, it fails to capture that. So what happens when you include this into the analysis? So you start with the data and you discover these 6 different types of relationships. And then you build a network. The network here would be the genes and the relationship with each other. But this is really big. So in order to simplify this, what you do is you try to use the equivalences to build clusters. So after you merge them using equivalences, you can have bigger clusters, smaller clusters, and then figure out how these clusters are related to each other in a big picture. So in the context of this disease, inflammatory bowel disease, this is a really complex disease. There are two types of IBD. One is called UC, and another is CD. This is ulcerative colitis and Crohn's disease. So in this case, we have 3 different kinds of samples: normal, UC, and CD. You could also divide into normal and IBD, and that's what most people do. In order to identify the targets for the IBD, they will say, okay, normal sample and IBD samples, and try to identify differentially expressed genes. In the Boolean analysis, we are not going to look at which samples are normal and which samples are disease. We assume that there is a mixture of samples in this data. There is a set of normal sample and there is a set of disease sample, and disease samples can be UC and CD. When you look at the relationship between genes, you are not looking at the labels. You're not looking at which samples are normal, which samples are disease. You're getting a bigger picture of how the genes are related to each other. So it's completely agnostic to these groups that are determined, and there is a lot of noise in these groups. And then you build this network, this complex network with directions, edges with directions that are determined from the asymmetric Boolean implication relationships. So I'm going to show you that we can figure out from this network something really useful, which is what would be a natural progression from a normal to a disease, a natural underlying time series that we can infer from the data directly without using the labels, without knowing where is the normal, where is the disease in a more formal way. So how do we do that? So we're going to come up with an inferred natural time series. So let's start with a simple path. let's say we have two clusters, X and Y, or two genes, let's say, for in this case, to simplify. And there is a relationship which is X low implies Y low, which looks like this. So X low implies Y low have one sparse quadrant, which is the quadrant number 1. And when you have this, you can see how can we orient the samples in a natural way. The natural order would be 0 to 3 or 3 to 0. You can't say 0 3 2 because that's changing, two variable at a time. So we assume that maybe the natural progression happens when one thing change at a time. Assuming that, you can say that either X change first or Y change first. And this happens in both directions. Either they go up or down. We don't really know because this doesn't give you the direction of the normal to disease or disease to normal, right? That happens from the labels. And if you have other paths, you can characterize in simple natural way. The thing is, when you have a more complex path, you can orient these samples at a much higher resolution. Because when you have this kind of relationship, let's say you have a high to high and then high to low and then low to low. If you have these edges in the network, you can figure out there may be 5 possible bins that you can think about. And these samples in these beans can be ordered in either this way or the reverse. Okay, so so you can figure out the 1 2 3 4 5 or 5 4 3 2 1. So these are going to the 2 possible ordering that you can come up with. So when we look at a disease like IBD, we'll start with the data, we'll build the relationship, and then come up with a network. And we'll start looking at the properties of this network here. In this case, certain clusters would be really big and certain clusters would be really small. If you look at the size of the cluster, you can see that there is a scale-free property that emerges, which is there is very few clusters with bigger size, and there's a lot of clusters with smaller size. This is in the log scale, so this is called the scale-free property. And then we'll start looking at the network. Because the network is big, we're going to look at only the top few clusters and starts looking at the relationship between these clusters and organize them with respect to the IBD process. So this is what the algorithm came up with. So you have, let's say, the top 6 clusters here, and this is how they are related to each other in a big picture. Then we'll do machine learning to figure out which clusters and which sequence of the clusters can be used to figure out the natural underlying time series in the disease from healthy to disease setting using AI. So in this case, we perform this analysis and figure out that this path 1, 2, 3. So let me go back to this plot. So here you can say 1, 2, 3 is basically a set of 1 is a set of genes, 2 is another set of genes, and 3 is other set of genes, and all of these are associated with healthy samples, most likely, right? So most of the healthy sample express these genes at a much higher level compared to these other clusters which are in the disease samples. When you look at the labels at this point. And so 1, 2, 3, when you look at the path 1, 2, 3 and try to figure out the natural underlying time series, it actually separated the normal and the disease cohort really well. And so these are the validation. You can see how they are able to separate the normal sample and IBD samples in a continuum from left to right based on this algorithm. it's not perfect, right? You can see there is a mixture of samples, but most of the cases you will see the IBD on the right side, normal is on the left side, and in the middle there is going to be some mixture. So this progression that we come up with, we can test whether we're not just separating the normal and IBD. Are we separating within the IBD certain characteristic? For example, maybe the IBD on the rightmost side is most aggressive, and the IBD on the left side of these, which are very close to the normal, are not that aggressive. They are most like normal. Uh, that's a bold step, right? We don't really know. We don't have this information from the clinic that well. So can the algorithm come up with these information? So if you look at just the normal and the disease, you can see for the UC and the CD, it all separated. The UC and the CD are both separated from the control, which is the normal, and there's not big difference between the UC and the CD in these cases. And with the ROCAUC of 0.81. Now, figure out the disease continuum. Within the disease, can we separate the aggressive and the not aggressive ones? And here I have compared this Boolean approach to the other approach, the differential analysis versus the Bayesian analysis, and try to figure out the list of genes there. You can see the Boolean analysis performs really well when you are challenged with the responder versus non-responder. So in this case, these algorithms were not given the responder and non-responder before. They were given the labels of normal and IBD on the cohorts and tried to see whether they can separate them. And these classification will be applied on the responder and non-responder and how well they are separating. In this case, the Boolean does really well. And in several other cohorts, it can identify the active and the inactive, or the responder to non-responder, well, within the disease cases. So these are all IBD cases. There is no normal here, right? So in these cases, even they're able to separate, the algorithm is able to separate the aggressive one. You could apply this also in the mouse model and then see which mouse model actually mimic what we see in the human setting. There's a lot of different mouse model for IBD. There are chemical based or genetic based, and you can see based on this particular algorithm, if you use the path 1, 2, and 3, the chemical and the other infectious model actually performs much better compared to the genetic model. The genetic model completely randomized the normal and the colitis sample. And this is actually an insight that you can get, that, oh, if you want to understand human IBD, you probably need to look at these other models as opposed to the genetic model. The grand challenge here is we have a lot of drugs available for IBD. There are many that are already approved in the phase 3, and they're basically approved after phase 3. And there's many drugs that actually failed during this phase 1, 2, and 3. And we know them very well. So these are the targets. You can see the top 5 targets here, and the rest of them didn't pass the phase 3 trials. So it's everybody's dream to actually come up with a target that will end up passing phase 3, right? But nobody knows what happens during this process and what determines a target to pass phase 3. There's a lot of complex thing that happens. And if you use the differential analysis, what happens is that most of these genes are differentially expressed in the normal and IBD. And that's not surprising because that's what people started with. So they are differentially expressed, and then we tried them, and some of them passed and some of them failed. But then people have this advanced approach, Bayesian analysis and other network-based analysis, and figure out, oh, let's see which is a better target, right? And the Bayesian analysis actually figures out that these are supposed to be the best targets, which actually failed. So these the 6 different targets that the Bayesian analysis figures out from the network approach failed in the clinical trial. So what happens when you apply Boolean analysis on this setting? It's really amazing. It's actually it can classify the targets perfectly. So whatever we think is a better target using Boolean analysis, it actually passes. This may be overfitting in some extent, but it's encouraging that that an approach that a new approach that looks at the natural progression of the disease and figure out which targets are better targets is able to separate these really complex processes that happens, and anything that we come up with here are likely to pass, so we can put more bets on these the outcome of the results of these analyses. So that's basically my talk. To summarize, I talked about Boolean analysis that discovers fundamental relationship between genes. So whenever you talk about these 6 different categories, we hope that they are fundamental, and in a big data setting, it's really robust, so that when you go to the clinic, you see the same thing. The analysis provides a way to order samples. So if you have disease normal and the disease samples, you could come up with an ordering between them, and also give it this ordering will give us insights into the continuum, the disease continuum, and also therapeutic targets. We see that these patterns are very strongly associated with disease phenotypes. So to acknowledge, so I have a lot of collaborators and mentors who helped along this process. Before I started this work, I didn't have any insight into IBD, so I had to learn these concepts. But at an abstract level, from a computer science perspective, you can categorize any disease into normal and disease settings, and try to dive down deeper by looking at these complicated relationship. I would say simple relationship as opposed to Pearson correlation, and come up with better insights for diseases. Okay, so that's basically before time, so I can take questions.
Okay, thanks, Debashis, for a really nice talk. So I would like to ask the panelists if they have any questions at this stage. Any of the panelists? No. Whereas if you see in the Q&A section, there is not many. All are there. They're asking about the Boolean network analysis. So they're asking for a good review paper per se. So anyway, so with this, I would like to thank Debashish again for having the time and the patience, because at his timing, it's like 6 in the morning.
Yes.
So thank you again.
5:30 to, yeah.
Yeah. Okay, so you can still have a look into the Q&A section if you think there are certain good questions that you would like to answer. And
Okay.
yeah, so with this, we end the second day of the summit. So thanks a lot to all the participants, to the panelists, to the attendees, and hopefully we save our energy for tomorrow. Thank you again. And please check
Thank you very
out
much.
the web page of the summit. You have the posters updated over there. You have the link to the videos as well as the PDF of the posters. You also have abstracts from the speakers. So yeah, thank you. And we conclude the second day. Thank you again.